This meeting is being recorded.
Okay, so let's look at the APT decode project. So APT stands for not advanced, enemy. It stands for automatic picture transmission. It's a form of, we're going to encode an image as sound. And this is very similar, if you ever heard of like slow scan TV, very similar to that. But this is almost exclusively used by weather satellites that are basically backwards compatible with like 1970s, 1960s technology, which basically means just the NOAA 15, 18, and 19. And I imagine they'll continue to. By the way, these images are very low quality that you get from the NOAA satellites. That's because if you want to get the high quality images, you have to listen on the L band. And I just showed you that antenna rotator. That'll do it. So the high resolution picture transmissions from the NOAA satellites operate at like 1.7, 1.8 gigahertz. And you can, I think it's closer to 1.7 gigahertz. But anyway, you really need a good gain, good directional antenna to get that, and you need it pointed directly at those. But anyone with a good 137 megahertz antenna can receive the APT signals coming from these NOAA satellites and decode them. It's great for students. The only thing is, of course, you have to wait for NOAA satellites to pass overhead. So there's a great site that's I use, N2YO, N2YO.com. And you can get a list of satellites, and you can set your home location. And so, of course, the NOAA satellites, NOAA 19, 15, and 18. So if we go to NOAA 19, we can get, it'll be tracked right here. And we'll go into how this is tracked later on, maybe. But what we can do is we can go click on the 10-day prediction. And that's going to tell me when it is passing and how good the pass is. So when you're looking at passes and how good it is, you want to look at elevation. Elevation is like, how overhead is it? At 90 degrees, that is a perfect pass. Don't miss it. You want to get that pass. You're going to get a very good signal. Something like 16 degrees, like this one here, is barely even a pass. Like, it'll show you the path here. So it's flying over Texas, which is kind of just over the horizon from my perspective. So I'm in California, the Bay Area. That would be not a good pass. But let's see, do we have, this one's 85 degrees. Oh, that one's really good. So you see this 85 degree pass right here? It's going almost overhead. And that is happening at local time. It's going to start at 9:01 p.m. So, 9:25 a.m. So this would be perfect. Perfect. This would be my pass I'm going for. And this is happening on the 18th. So I'd have to wait a few days for this perfect pass. And that's what's so frustrating about these low Earth orbiting satellites getting a good pass, is that sometimes you just have to wait a few days. Now, you do have a few options. You do have NOAA 15 as well as NOAA 18. 15 is starting to get a little wonky, but 18 is still good. And so we can go check to see when that's passing overhead. Anything sooner? That's good. Oh, that's passing overhead today at a little after this ends. So 11:37 my time. So if I wanted to, I could get a nice image from NOAA 18 today. And it's not random, obviously, when they pass over, but you're going to have droughts where like you're just not going to get any good passes for a few days, and then you might get like 3 good passes like lined up within an hour of each other. So, it's frustrating. Anyway, like I said, all you need is an FM you need an SDR that can receive FM signals. So basically an FM radio that can receive on 137.1 to 137.9 megahertz. So there's a link to download a WAV file on the project page, and we can click to download that. And if we open it up, it's apt.wav, so we'll unzip it. In fact, I'll just share my screen so you can see what I'm doing in full, even though it'll be a little small. Let's see, stop share. Share screen. Screen 1, here we go. So I'm sorry, it's a little bit small, but I downloaded apt.wav, so we'll extract all. Okay. And now we get apt.wave. And we can actually open this up in any audio player. And let me put my headphones up to the microphone so maybe you can hear it. 1 second. So it's just an audio file. And the reason why I would send the raw like IQs of like radio signals being sent out, except that it gets into the gigabytes of length. So I unfortunately, we're just going to start with the audio here and not go through the process of decoding from a raw radio signal. But so we have this audio file that just sounds like a bunch of beeps. And like I said, you can open up in any audio program, play it back. And the clicks and beeps you hear are signifying a new line of the image. And just to be clear, this image is not from a satellite. I generated this image myself. And so you can download some free software that can decode this image called NOAA APT. I've already downloaded it. You can go to the web page. Actually, let me just share my browser again. 1 second. Share screen. There we go. That should be a little better. So you can go to their website here. Go to the releases page on GitHub. And then depending on your operating system, you can download, usually if you're running Windows, you'd run download the Windows version. They have, they don't seem to have a Mac version, but they do have a Linux version. So you download NOAA APT, and then we're going to run it. So let's do that. So once again, I'm going to stop my share my full screen so you can see what I'm doing when I launch the program. So I already downloaded NOAA APT from earlier. So you just unzip the file, go into the folder, and you're just going to double click on noaapt.exe. And now we'll switch back to the just NOAA APT. Yeah. So this is the program, and we're going to decode the file. So the input file is the file we downloaded. So I'll go to my downloads folder, which is actually on my storage drive, apt.wave. So we open up the wave file. We're going to click decode. Processing, we're not going to do any processing. This actually is not from a satellite. I made this image myself, and we're just going to push process. And it is a little bit, oh, so this is upside down. And this is because sometimes the satellites are, passing from north to south and sometimes from south to north. And so there is a way to fix this. Up here where it says rotate image, we're going to say no. And we'll process it again. There we go. And then we have the text here. It says, welcome to the space. And this is the flag. And you can save the image if you want by going here to saving, selecting the output file name. So we'll go to the desktop, image.png. Okay, save. There we go. Now we have an image on the desktop of what we just decoded. And I assume you know how to enter the scoreboard, or submit the flag. But just in case you don't, let me share this again. So Sam wrote some awesome software for submitting flags. So we go here, and you would select. Let's see, this is space, so SP100. So we would select SP. This is challenge. Let's see. SP100. Welcome to these. Samples a complete me. I think there's like a test or something we could use as a name, but I think delete me is fine. Welcome to the space. Put submit, and then it says answer correct. So that's how you submit the flag for exercise 1. And then let's continue. Let's do an introduction to GNU Radio. So I am going to share a Linux desktop here. Share screen. There we go. I'll actually visit my website, or Sam's site from within Linux here. Samsclass.info actually. All right, so let's see, we want to go to in space, no one can hear you hack, and GNU Radio. So this does not, normally GNU Radio, you would hook up to an SDR and listen to software. However, this project does not require any external SDR, so it's a good way to get started. So in Linux, we are going to install GNU Radio. I don't know if it's already installed. Apt GNU Radio. Yes, so it's already installed. Perfect. So I already have GNU Radio installed in this version of Linux. So we're going to start GNU Radio Companion. Yes, I just started a GUI application from the command line. Hopefully it'll start. Here we go. Perfect. So this is what GNU Radio looks like when you start it up. You have this sort of work area where you sort of draw your diagram to the, this is your main work area. And to the right here, we have a whole bunch of components we can throw in. So you can see a lot of this stuff is going to be pretty advanced, if you want to do like Fourier analysis, which is very important in radio, but a little past 101 type stuff, various types of modulators, once again, a little past 101, digital television. Yeah, a little past 101. But we can do some very simple things here, like just playing with waves. And that's what we're going to do in this project. So we have GNU Radio Companion open. Oh, by the way, yeah, down here we have a console, as well as some data that you can edit in the bottom right-hand corner. And let's see, to start, let's go File, and yeah, let's save a new file on the desktop. Yeah, we're going to do new Qt GUI, yeah. And we're going to save this as, save this on the desktop, sample, DRC. By the way, what this is doing behind the hoods is that you use this to like draw diagrams. And what it's going to do is it's going to use that diagram to generate Python code to manipulate radio signals that come in. So it makes it really easy to do custom decoding of radio signals. So if you kind of know what the signal is, or you have a rough idea of, how to decode it, or just want to play with it, and there's no like there's no prefab decoding software, you would almost certainly go to something like this, like GNU Radio. There's also MATLAB and Simulink, and there's a few others too. I think GNU Octave can also do some radio stuff as well. But GNU Radio, I think, is the most popular. I mean, every time I see people do radio hacking, it's almost always in GNU Radio. So, all right, let's continue. So we have this new project, and we're going to create a tone, right? So instead of creating like an incoming radio signal, we're just going to create a sound wave tone, like a C chord or something. So we're going to start by double-clicking on the options block which is this top left block here. I'm going to double click. And we are going to, let's see, I wrote this instruction, so I should know off the top of my head, but I don't. We're going to set so the ID needs to be changed to something new. And let's see, what do we set it to in the example here? We're going to set the ID to tone. Okay. The ID usually has to be unique. And then we'll click OK. And now we're going to add a signal source, which, let's see, that is in the waveform generators. Okay. So we're going to add a signal source right here. We're just going to, so I click on signal source and I just drag it over here. So this is what a typical block looks like. There's sort of an input and an output. An input being a frequency and an output. And based on the color, we'll tell you what kind of data it is. So I believe blue is a complex number. I'd have to double check off the top of my head. Properties, signal source. So let's, we're going to double click on the signal source block and set the frequency. Frequency, we're going to set it to, what do I have it in the example? 261. Okay, 261. 626. And instead of having a complex number be sent out, we'll just have a float. So it'll just create a simple float, a single number coming out that's essentially a cosine at a frequency of 261.626, which is well within human hearing. We'll push OK. And now you see the output changed the color. It changed from blue to orange. That's because now it's a float output. So the project talks about the different colors here. So yeah, orange is a 32-bit float. And now we're going to need an audio sync. Okay, so an audio sync is basically, think of it like your speaker. So we're going to create an audio source that's a 261.626 hertz signal, and we're going to send it straight to our speakers. So we'll go to audio sync, throw that here. And notice that the input is also orange. So that means it's taking a 32-bit float input to send to the output. And so what we're going to do is we're going to drag an arrow from the output of the signal source straight to the audio sync here. So now we have this nice little arrow saying signal source to audio sync. Anything else I want to do? Yes. Okay, so we're done. We'll just push play. And you should hear a tone. And this is going to get loud. Hold on. Missing. Xterm is missing. You can change the setting in conf, or I can just, Okay. That was loud and obnoxious, but yes, I did it. I made a tone using Gnu Radio, played over my speakers. It was not fun. Oops. But it works. It works. We got a tone. Awesome. And one of the things you can do in GNU Radio that's very powerful is you can set up these GUI blocks that allow you to sort of view what's going on during the different parts of the signal path. So if you want to see like what, if something's going wrong, if you're decoding things properly, you can set up these GUI things. So we'll go to the instrumentation down here, instrumentation, instrumentation, there we go, QT. Okay, and we're gonna want, let's see, this example, we're using the GUI time sync, okay. So this is essentially, if anyone's ever used an oscilloscope, that's what we're doing here. We're making an oscilloscope. We're gonna change the type to float, okay. And we're gonna drag from the output straight to the GUI timesync right here. And now, because I was complaining about Xterm, I'm going to very quickly just install Xterm for it. So update and sudo apt install Xterm. No one steal my password, please. Okay, we just wait for it to update. Oh, it's installed. I don't know why I was complaining. Anyway, we'll play it now, and I'm going to take off my headphones because this is going to get loud again. But we're going to see a GUI pop-up showing us the waveform in real time.
Yeah, that's
Oh boy, yeah, that was fun. All right, but yeah, so we've created a waveform, we can hear it, and we can see it, which is very useful. All right, let's see, what else can we do? The first flag is the text under the green in the screenshot below. Okay, so the first flag, I'm going to run it again. So if we look at the screenshot here, it says not something yet. Let me run it. You'll see what it is. So the first flag is titled, not titled yet. The first flag. So, okay, so we have this set frequency. It makes a tone. It's an annoying tone. But, you know, the real magic of GNU Radio is that it's programmable. We can make it anything we want. So we can control the frequency. So what we're going to do is we're going to drag a GUI widget called the Qt Gui Range widget. So let's see, not audio. Let's see, where is it? Again, it is GUI widget. Oh, GUI widget. Here we go. Qt GUI Range. There we go. So this is the GUI Range widget. We're just gonna, I'm gonna drag it up to the top left here. There's no inputs or outputs, so that's fine. And then what we're going to do is we're going to set the ID. Okay, so we're gonna double click. So I dragged the Qt GUI Range block up here. I'm gonna double click on it. I'm gonna change the ID to something a bit more descriptive, and I wanna make sure it's the same as, okay, so I'm gonna change it to tone frequency, because that's what we use here in the example, tone frequency. We're gonna set the default value to what we had before, 261626, which I believe is middle C. 261626 to type float, perfect. And we're gonna have a start and stop value. So we're gonna set the minimum value to 10 Hertz, and we'll stop at 20,000, which is pretty much the limit for human hearing. Really, it should be 20 Hertz, because that's pretty much the limit of human hearing. And let's see, anything else we want to set? No, I think, oh, step size to 10. So we're going to go up in increments of 10. Perfect. All right. Oops. Let's do that. Right. And so what we're going to do is we're going to set the frequency to the ID of the Qt GUI range. So we're going to double click on this, set the frequency to tone frequency, which is the ID of that. And push OK. All right. And now if we push play, and I'm going to take off my headphones again, we should have a slider, and I will be able to control the frequency. And there we go. We've just made it interactable, so we can control the frequency that's being generated. And then, of course, if you get more fancy, you could probably make a little music box or something, but that's a bit out of the scope of this tutorial. I'm just trying to get you introduced to the concepts of GNU Radio. So like I said, behind the scenes, what's going on is that we're using this sort of GUI editor to generate Python code for us. And so if we go to the folder where we saved, I'm going to save it again. And that was saved on the desktop. So if I go to the desktop, I see tone.py. So instead of going through the GNU Radio interface, I can just type /tone.py and run the program straight from the command line. And it absolutely worked again. And of course, you can edit the program and add any Python stuff you want to it. And let's see, flag 2, the Python code. Okay, so there are comments at the top of the Python script. So if we type head tone.py, yep, there we go. The flag is GNU Radio. This right here. And that is how you get started with GNU Radio. Now, when you're using this in the field, instead of having a sort of arbitrary signal source, you would actually have a radio source, and then you would manipulate the radio source. And one of the things I think I'm going to just have to do, because I was hesitant to do this because most students don't have SDRs, but once you get past this point, you really do need an SDR. I'll show people how to make simple AM receivers, FM receivers, listen to the radio, just using GNU Radio. And of course, you can get more complex and start doing things like watch TV through GNU Radio or decode TCP stuff, you know. Modulate. Oh, you can also, if you have a SDR that can transmit, you can send out signals as well. So yeah, GNU Radio is the most important tool that when you start getting beyond the basics. And then let's see, let's go on to two-line elements. I don't want to spend too much time in GNU. There is an example within GNU Radio using decoding BPSK. However, I do want to introduce you to two-line elements, which are incredibly important, and you're going to run into very soon when you start tracking satellites. So we saw earlier, I went to this site called n2io.com. n2io, and you can track satellites. So METOP is another weather satellite, very wonderful images. And we can see where it is over the Earth right now. And we can, of course, get predictions. Oops. No, go away. We can get predictions for it. So how does all this work behind the scenes? How does this site know where the satellites are? And how is it able to make these predictions? Well, it's downloading something called two-line elements, or TLE data, from a standardized source. So one source that I really like, or that I use a lot, is called CelesteTrack. Let's see, yeah, CelesteTrack. This is a NORAD sort of database of various different types of satellites and their TLE data. So if we look at, let's see, TLE, new way to obtain, where is it? Current data. Oh, here we go. Let's look at Earth resources satellites. So you have these data files that downloaded straight from NORAD or celesttrack.org, and these contain a list of satellites and a whole bunch of numbers. And these are called two-line elements. And so these come from old punch tapes, believe it or not. When satellites were first being tracked in orbit, the numbers would have to be punched into tape into two-line elements, which is what we have today, which is why they look the way they do. And this is actually three-line elements because you have the name on top followed by the two-line elements. And these numbers mean a lot, but they're like sort of pre-computed figures, which we'll get into a little bit, but it basically describes the orbit of the satellite. So if you wanted to see the current satellite, current orbit of RaySat, right here, this is RaySat. These numbers describe its current orbit. And by the way, all of these orbits are based on a current sort of time, I would say. It's the correct word is epoch. So all this data, you need to download the most recent data. All this data is good for is 2 weeks max, at which point just random fluctuations, makes the data unusable anymore. So there's lots of things affecting spacecraft orbits, and it just has to be constantly updated. So if we go back to two-line elements here, I have an example of the two-line element from the ISS, Zarya, and all these numbers here. So the first line here is this ISS Zarya. This is just the name, right? And then we have the first line here. So the first number we see here, 25544U, that is the NORAD ID. So NORAD keeps a universal ID of each object in space. And this is the ISS's ID. That's all it is. And then the U means it's unclassified. So depending on what's in orbit, it can be classified, secret, or unclassified. So everyone knows about the ISS. It's unclassified. This is for everyone. And then the second thing here is the international designation ID. So this is just another way to reference the satellite. So none of this data so far have anything. The first three pieces of data are just the ID, just what we're looking at. And then we have this number here, 20330, and that's the epoch date time. So like I said, this data is only good for a certain amount of time. So this specific data was from the 330th day of 2020. That's what it means. And then we have a whole bunch. Now we start getting into the orbits, and they're all like pre-computed, and they're all designed to be like computed by hand, I would say. So there's a lot of weird terms that make it very easy to compute the orbit, but are weird, like kind of names. So you have like the first time derivative of the mean motion and the second time derivative of the mean motion, which has to do a lot with like drag and stuff. So like how much is it slowing down or speeding up? And you have the B star drag coefficient right here, which is, so with low Earth orbiting satellites, they are in space, but the boundary between space and Earth is wibbly woggly. So the atmosphere will like expand and contract, and it'll drag on low Earth orbiting satellites and slow them down. And so that's something you have to keep in mind when you're tracking these satellites. And so the drag coefficient is right here. And then we have the ephemeris type, which is almost always 0. And then a checksum. Okay, cool. And now we're getting into line 2, which has a lot more data about the current orbit. So once again, we have the NORAD ID, copied straight from the line above. And then the second thing here is, let's see, that is the inclination. So the ISS is currently, or it was in 2020, orbiting at an inclination of 51.6456 degrees. So it's not in an equilateral, orbit. It's at an angle. It kind of goes up and down. And if we go over to N2IO, we can actually see that. We have something in the chat. Do they use time difference between the expected and received? Yes. Well, not the drag, but in fact, I don't even know how they specifically determine the drag coefficient, but we can talk about Doppler shift in a second. So when anything so spacecraft are moving fast enough and our radios are precise enough that when the spacecraft is moving towards you, the signal will actually be shifted higher in frequency when you receive it. And when the spacecraft is moving away from you, it'll be shifted lower slightly. And that is something you do have to be aware of when you are recording signals from spacecraft. Now, that is not used to calculate drag as far as I know. I think that there are just ground station trackers. They're just keeping track of where things are and how they're moving and calculate based on that, as far as I know. But absolutely, you do need to pay attention to Doppler shift when you are recording signals from spacecraft. Though I will say for the simple stuff, for APT, automatic picture transmission, don't worry about Doppler shift. As it shifts, just make sure that your bandwidth is large enough to get the full signal and you'll be fine. Don't worry too much about that for right now. Worry about that when you start working with very weak signals or more advanced signals. So yeah, I'm going to go to N2YO to look at the space station, n2yo.com. And we'll go to the most track. I'm sure the space station is there. Yep. And so if we see the orbit of the space station, sure enough, you see how it makes that sort of sine wave pattern? That's because it does have an inclination of about 57 degrees. So it's sort of bobbing up and down around the equator. Let's go back to the TLE. So now we have 267.7478. What's that again? That is the right ascension of the ascending node in degrees. So that's essentially where it passes the equator when it doesn't incline. The eccentricity of the orbit. So the ISS is in a roughly circular orbit, but not precisely. It's very hard to get a precisely circular orbit. But it's 0.01905 eccentricity, so it's a very circular orbit. Argument of perigee in degrees. So that is sort of where the perigee is in terms of, so the closest point of the orbit, where it is sort of relative to Earth. Let's see, 12. What is that? Yeah, 12.7. Well, that should be the mean anomaly, which is kind of where it is in the orbit as well. You have mean rotation, aka revolutions per day. Yeah, here it is. So that's the last thing. So it orbits 15 times a day. And then there's a checksum at the end, one. Anyway, so it's just a bunch of orbital sort of data, and that you can use to calculate. You take this data, and this is what it was at the time. Like we said, there's an epoch. So when this was taken, this is what the orbit looks like. Okay, then if you take Newton's equations, you say this is what the orbit looks like right now. Let's plug this into a calculator, figure out what it's going to look like in 10 minutes, 20 minutes, a day from now, 2 days from now. And that's how TLEs work. So you download the TLE data, says at this point in time, this is what the orbit looks like. And now you can sort of figure out what the TLE data is, or where the spacecraft is going to be, just using Newton's laws. I have a nice picture there. I forgot I put a nice picture that I stole from, I think, Wikipedia or something. The flag 1 is the full year. So like I said, you have to extract this from the TLE data. This is the Hubble Space Telescope. You would have to extract this from here, which should be, let's see. Yes, it should be 1998. This is what the 98 stands for. Yes, there is in case you're wondering, there's a Y2K bug in TLE data, essentially. They're just using the first two numbers of the last year. Like I said, this was made for this data was designed to be used with punch cards. So much of the stuff is outdated. It's fantastic. Use a search engine to find the name of the satellite with the NORAD ID. So we know that the NORAD ID, and this one is 44352. So we'll go into Google and say NORAD ID 44532. That is the Armadillo satellites. Once again, this takes us to N2YO. But yeah, that's the NORAD ID for the Armadillo satellite. I just like that name, so I threw it in the project. And then I have a project here where you can use Python to extract TLE data. So to do that, you are going to install Python, and we're going to use a library called Skyfield. And so Skyfield is, if you're doing any sort of like astronomy or orbits or anything, and you need a Python library to help you with that, Skyfield is, the library for you. And we're going to use that to deal with our TLE data. So let me see if I have this installed. Python 3, that's installed, okay. Search Skyfield. Can I install it? No, I cannot. So sorry about that. We'll use pip to install Skyfield, Python 3. As module pip. There are commands like pip3 from the command line, but I really like running pip from the Python I know that I'm running. Like, I don't know, I'm just weird like that. Anyway, so if you Python 3-m pip, module pip, you can then just run install Skyfield, and that will, okay. I don't have pip installed, so apt search Python 3 pip. I think it's just be Python 3-pip. Yeah. Apt install Python 3. For some reason, a lot of students really like to see me troubleshoot things. I've noticed. So hopefully you're not too bored. So if it says pip's not installed, you probably just have to install pip. And sure enough. Yep. Now we'll just run the command again. Python 3 module pip install Skyfield. There we go. Now Skyfield is installed. So we're going to create a new document here. I'm going to open up Mousepad, and we're going to call it tle.py. And can I make the font really big? That's what I want to know. Edit, preferences, editor. Window, color scheme. Oh, no. I want to use size 16 font so we can all see what I'm doing. Size 18 is even better. Ooh. Okay. Oh, yeah, that's a nice big font. Okay, perfect. So you can all see what I'm typing. So I'm just going to copy and paste this code. Not even going to bother changing anything. So we're going to copy and paste that into our text editor here. We'll take a look at what we did, and we'll save. So we're running Python 3, shebang. We're going to import Skyfield API and elements lib. And by the way, if you want to know how Skyfield works, or the documentation, you can go to the Skyfield Python documentation. There we go. So this page has everything, and it'll tell you how to, it'll give you a couple examples, like you can make a program to see when it's going to get dark, when Venus is at the greatest east and west elongation, et cetera, et cetera. And they also have, of course, the full API reference here for doing things like vector functions, Earth satellites, Kepler orbits is what we're interested in. We're interested in Kepler orbits. Looking at constellations. So anything with space, you can use this, or astronomy. Skyfield is fantastic. Anyway, so back to the code. So we import, our standard imports for Skyfield, sys, math. Okay, perfect. Now we put the TLE data into just a regular string. So we're looking at the ISS. And then we're going to just make sure our input is, so this code right here just makes sure that our input is valid, that we're not putting in unknown weird TLE data. And satellite equals, okay, so we're going to extract the satellite data. And yeah, so now this is how we get our satellite data. So we'll run it. Nothing's going to be printed out, I don't think. So we're not, chmod 8 plus 8 x TLE.py, but we shouldn't get any errors, which is the most important thing. So yeah, so it works. We're not getting any errors, so that means we decoded it correctly, but we're just not doing anything with the data. Awesome. I meant to do that. So we have some working code here. So we're going to continue. And most of these are just, I know this looks like a lot of code. It's just printing data. All the hard work's been done. So after all this, we're going to let me make sure I'm doing this correctly. Yeah. We're going to have to, unfortunately, let's see, thanks again. Gotta go. Okay, see you later, David. So I need to indent all of this, unfortunately. There we go. Go. Ay. Oh, that's indenting. Can I multiple indents? No, I can't. I probably should have used a Python editor for this. I know, so fun, huh?
That's what I drag about Python.
Yeah.
I spend a lot of my time doing this.
If you use a better editor, you can do this automatically. Unfortunately, I didn't think that far ahead. And always have a new line at the end of your file. Okay, there we go. So now we'll run tle.py. See if it works. There we go. Ah, it worked. First try. How fantastic is that? First try, it works. So we got some output. So what happened? So we decoded the data, and we print the satellite name, and then we print the NORAD ID, the international classification, and this is how we get all the data out in the epoch time. So we can see here that we indeed got the NORAD ID out. It's unclassified. We got the epoch time. So this was from 2020 at 2600 hours at 17 minutes, and we have all the data here for us to see. Cool. All right. Now we can work with TLE data and just get it out and do Python with it.
Well, I think we better stop there, Caitlin. We're hitting about the end of the time here.
All right. But yeah, that's some of the most important 101 topics in space hacking that you should absolutely know.
Well, I'm going to stop the recording.